Hi everyone. Today let's look at a classic problem, palindrome number. Opening, we are given a non-negative integer, dot, and we want to decide whether it reads the same forwards and backwards. As an example, the number 1221 reads the same in both directions, so it is a palindrome. The number 121 also does, but the number -121 does not, because of the minus sign, and the number 10 does not, because its reverse would need a leading zero. We want to answer this without converting the integer into a string. Naive approach. A first idea is to reverse the entire number and compare it with the original. We peel off the last digit, build up a fully reversed copy, and then check whether the two are equal. This is easy to follow, but it walks every digit and stores a second number just as large as the first. We can do better by reversing only half of the digits, because a palindrome is defined by its two halves mirroring each other. Core idea. The key insight is that we do not need the full reversed number. We only need the second half, reversed, to compare against the first half. So we peel digits off the right end of the number and pile them onto a growing accumulator, one digit at a time. Each peel shrinks the original number from the right and grows the accumulator from the left. So the two values march toward each other. We stop exactly when the original is no longer larger than the accumulator, which means the two halves have met or crossed. At that point we compare, and the comparison tells us whether the digits mirror. Key details. A few details keep this correct. First, the guard at the top. Any negative number is rejected outright because the minus sign has no mirrored partner on the right. Any positive number ending in 0 is also rejected because its reverse would need a leading 0, which a normal integer cannot represent. The single number 0 is the exception, and it is a palindrome. Second, the stopping condition. We keep peeling only as long as the original number is strictly greater than the accumulator. This naturally lands the two halves at equal length when the digit count is even, and leaves the accumulator one digit longer when the digit count is odd, with the middle digit sitting inside the accumulator. Third, the comparison. When the digit count is even, we check whether the two halves are equal. When the digit count is odd, we drop that middle digit with an integer division by 10, and then check whether the two halves are equal. Walkthrough. Let's trace the first example. We are given the number 1221, 4 digits long, and we want to decide whether it is a palindrome using the half reverse method. We enter the function with the number 1221. The first thing we do is run the guard, which rejects negative numbers and positive numbers that end in 0. We check the first half of the guard. Is the number negative? 1221 is not negative, so this part is false, and we move on to the second condition. We check the second half of the guard. Does the number end in 0, and is it not 0 itself? The last digit of 1221 is 1, not 0, so the trailing 0 test is false. The whole guard is false, so we proceed to the half reverse loop. We set the accumulator to 0. This accumulator will collect the reversed second half, one digit per loop iteration, as the original number shrinks from the right. Now we check the loop condition. Is the original number greater than the accumulator? 1221 is greater than 0. So the answer is yes, and we enter the loop body to peel one digit. We peel the last digit of the original number. The last digit of 1221 is 1. We append it to the accumulator, which means we multiply the accumulator by 10 and add the digit. 0 times 10 plus 1 gives 1, so the accumulator becomes 1. We drop that last digit from the original number by dividing it by 10 and keeping only the whole PA. RT, 1221, divided by 10 gives 122. The digit 1 has now moved from the right end of the original into the accumulator. We check the loop condition again. Is the original number 122 greater than the accumulator 1? Yes, it is. The two halves have not met yet, so we peel another digit. We peel the last digit of the original number. The last digit of 122 is 2. We append it to the accumulator. 1 times 10 plus 2 gives 12. The accumulator now holds the reversed second half, which is the digits 2, 1. We drop that last digit from the original number. 122 divided by 10 gives 12. Now, the original number is 12, the first half, and the accumulator is 12, the reversed second half. We check the loop condition again. Is the original number 12 greater than the accumulator? 12? No. 12 is not greater than 12. The two halves are now equal in length, 2 digits each, so we stop. The half reverse is complete. We compare the two halves. Because the original number had an even digit count, we use the direct check. Is the first half equal to the reversed second half? 12 equals 12, so the answer is true. The two halves mirror each other. The comparison is true, so we hand back true. The number 1221 is a palindrome. Notice the structure of the whole trace. The guard let the number through because it was neither negative nor ending in 0. The loop then peeled 2 digits, one from the right of each half, until the two halves met at 12 and 12. Because the digit count was even, the direct comparison was enough. With no middle digit to discard, we reversed only half of the digits, and the two halves mirrored each other exactly. Complexity. The running time is proportional to the number of digits. Each loop iteration peels 1 digit and shrinks the number by 1 digit. And we stop halfway through, so the total work scales with half the digit count, which is still linear. The extra space we use is constant. We keep only the accumulator and the shrinking original, plus a few temporary values. So, no matter how large the input, the memory does not grow. Summary. Palindrome number comes down to reversing only half of the digits. The ideas to remember are these. Negatives and positive trailing 0 numbers are rejected by the guard. With 0 as the special exception, we peel digits from the right of the original and pile them onto an accumulator, stopping when the two halves meet. When the digit count is even, we compare the halves directly. When the digit count is odd, we drop the middle digit before comparing. Thank you all, and see you next time.